this is an odd thing, or this is a special consideration, I made marks in there and I kept them. I'd suggest you do the same. Maybe you can do it on a PDF copy too, but those notes, years down the road, you'll find are essential. One other thing, when I was going through undergrad, I mean, I did sell back my health books, we had to take health course, and there's stuff I'm never going to use, but I kept all my engineering books, physics, and the only book I don't have is chemistry, and I wish I did, because the one thing I found, I hated chemistry, when I got to graduate school, I took crystal chemistry. A guy named Linus Pauling, who won a couple of Nobel Prizes, wrote stuff about the nature of the chemical bond, and it all came together and made sense. Just brute force memorization, I hated. Do you all have chemistry yet? How many had maybe a little dislike for some of the memorization? Anybody? If you did organic chem too, you probably had more than a little dislike. Phenomenal amounts of memorization. It's valuable though. When I did my master's work, did a lot of work with solid state physics, VLSI, fabrication, and plasma etching. Chemistry became essential to really understand. But crystal chemistry is more something that was beneficial to me, and I really enjoyed it in grad school. All right, now, see, the last thing I'm going to do is, are there any questions about this at all? About the book, the course? I think I laid it out pretty well. Please attend class. I prefer to record these lectures. Are you recording now?
Yes, I am.
Do I need to wear a mic or can you hear me?
I think for like just the sound quality in the video, I think you should wear.
All right, look, if I need to, we'll figure it out. But
okay.
I mean, you, like in the classrooms this summer, I was a lot closer, and I don't think there's a problem. But if I do, I'll be happy to. That mic doesn't work, we found it. And pardon me?
That's okay. I mean, like, it's no rush, but yeah.
Yeah.
Also, it said your Canvas wasn't active when I tried to set out for group meetings, so
Isn't Canvas, was this thing not on Canvas? I mean, isn't this course, it's not published yet?
No.
It is?
It is. For mine, it said it wasn't. For mine, it is. Okay.
I'll bet you something. I bet you this might have been a timing. Just take another look. Okay. And I've had a lot of problems with Canvas in the past. That's the only reason I don't use that. And that's honestly, it's probably a lot better now. During COVID, it was a disaster. So, and that's the other reason I did these lectures, video recording. I learned about Zoom. Zoom, after 1 year, your lectures are gone. In YouTube, this will be on YouTube. I can go back 15 years ago, stuff I put up there, it's still visible. I can go get it, and you can go get it. So that's the reason I do what I do. I don't even know if the university would allow me to record this whole thing on Zoom, but I prefer a student do it, put it on YouTube. One other thing I found out, that YouTube pays you when you get a certain amount of views. Do you know about this? So a couple of my students are making money on these lectures. I don't care, have at it. I mean, I don't know what the threshold is, but they're on things like signals and systems. We get large numbers of students. And you can't recommend it. Go, it's yours. Keep it. Okay, so now, you don't have your book. I'll post the homework though, and he's going to send me the PDF, I hope, right? Andrew?
What?
You're going to send me the PDF of the book?
Yeah.
Okay.
Sorry, I was looking at the Canvas.
Take a look. And I'm fairly relaxed about this. If you have a question when I'm doing something, you can ask me. Don't worry about that. This is not just a lecture. All right, it's interaction. I prefer interaction. I'll ask you questions. So the first thing I'm going to do is talk about how this thing is, really what we're going to do generally in this course. In the beginning of the course, what we do is we start by talking about transmission line theory. Now, how many in here have had circuits with Dave Irwin or something like that? Everybody should have had circuits in this course. If you didn't, come see me afterwards because you shouldn't be here. In circuits, you learn about things called lumped element parameters that really are associated with the real world. Do you remember the resistor, right? A resistor was a squiggly line like this. It was just like this. This is the simple other way. This is a new marker. It just goes to show you how things sit on the shelf during COVID and they're reused. This happens to me all the time. Let's see if I got one here that works. Well, that ain't gonna work this is a typical symbol for resistor, right? That's a lumped element, and normally, are you teaching in here, Dr. Gross? Yeah, he's one of the younger people we have. Anyway, when you take a look at this, right, if we have a voltage V of t, we know we get a current I of t here, simply V of t over R, right, and that's time, but this is nothing special right here. But one thing for sure is that resistor could indicate almost anything. It could be a light bulb, it could be, did you leave something here? Oh, your hat, okay, never mind.
Sorry for interrupting.
Don't worry, it's all right. By the way, I think he's 85, and he's been teaching since I got here. And when did you start here? I guess, I'm not at the level, right? Anyway, so you all remember that, right? But that resistor could indicate anything. It could be a light bulb, it could be a heating element, it could be anything at all that has that property. V is equal to, or really, V is equal to, or I should say, I is equal to V over R. Y'all with me on this class? That's just a representation of something that you don't care what it is, you just care about the properties. Another thing you learn about is this, right? L. And if you take a look at the actual relationships between V and I, there's a voltage here. Well, this is the same voltage there. We'll call it V of t. That you're going to get a current I of t, and that was equal to L d. I'm sorry. Wrong. V is equal to what? Y'all remember this? If you have, can you all see this okay, by the way? All right, this is an inductance L, and if you look at the current relationship I of t, it's really L di dt is equal to V of t. Y'all remember that? When you think of inductance, what comes to your mind? You usually have something in your back of your mind. How about a coil of wire, right? Isn't an inductor really just a coil of wire that it'll have magnetic energy associated with it, right? Without getting too deep into physics? A coil of wire. That's all it is. But it could be anything. Wire, straight wire has inductance. Coiled wire has inductance. Matter of fact, anything that conducts real current and creates a magnetic field around it has a certain amount of inductance associated. The other thing you learn about is capacitance. This is real just basic stuff. And if you talk about a capacitor here, and talk about I of t, then you know that I of t here was C dV dt. I'm being very, very just casual about this. I'm not trying to, but you all realize it, right? What's a capacitor to you, in your own words? Anybody? A couple of parallel plates that are insulated. You put a voltage across it, it induces charge, right? That's what a capacitor is. But it can have any shape. Anybody ever make a capacitor? They used to do this kind of stuff in physics. If you take wax paper, which is an insulator, and aluminum foil, you cut a piece of aluminum foil, put down wax paper, then put another piece of aluminum foil on the top of it that wind it. Now the aluminum foil on the inner and outer sheet can't touch. You wind it up into basically like a roll, like about that thick. Cut it off at about a 1 meter or maybe a 1 foot section, and you can measure the capacitance of that. It's surprisingly large. It doesn't have much breakdown street, but then you can discharge it. So they do that to get you a mental image of like a capacitor and the behavior. All right, now with that in mind, now I'm going to get into how we describe something called a transmission line with lumped elements that you're used to from your circuits courses. And let's see here. Try to get a dark marker, but I got a bad feeling about this. I'll try this one. So, when you have a transmission line, the only thing it means is, for us, it's something with a constant cross section. For instance, a coaxial cable. Y'all know what coax is? What? Got an inner conductor, an outer conductor. It's got some insulating material between it. like the route cable that comes to your apartment or your house, the Spectrum or Verizon or whoever is coming and using it, the cable or WOW, whatever, whoever does this, y'all with me? That's a transmission line. Another transmission line could be two parallel wires, like an extension cord. The cross section of that is always constant, doesn't vary. And because of that, there's also the flow of current that would go through there. What you can do is this. You can say, if I have a transmission line, I want to just show you it's two wires like this. And I'm going to say, I'm just taking a look at a length of it that is going to be delta Z in length this way. Now, these two wires don't represent anything special, except for the fact that we're going to assume that there's a voltage here, some V of Z here, and there's going to be a current flowing in it, I of Z. So there's a voltage difference and a current flowing in it, okay? Now, anytime you have current flow, now we're going to model this with lumped elements. Anytime you have current flow in any kind of wire, you generate a magnetic field. Anytime you generate a magnetic field, you're going to have magnetic energy, and thereby you're going to have an associated inductance. Do y'all follow the reasoning behind this? I should say one other thing. We're going to only talk about currents that are in a standard transmission line. It works in the differential mode. It means you're going to have a current here, some I of Z, and the same exact current will flow here in magnitude opposite direction. Think of an extension cord. Y'all with me? Current goes down one side, flows back the other, same amount at any point there. Y'all with me, class? I know we're going to model it. So here, I know if current's flowing this way, if I wanted to model this with lumped elements, I would have to have an associated inductance. So you're going to have some inductance per meter. They prime these coordinates. I'll stop priming in a second. It's assumed it's the inductance per unit meter. Y'all with me, class? Now, if we have current flow and it's a wire, doesn't matter how good it is, it has some inherent resistance. Y'all with me? Copper has resistance. It may be very small, but it's never zero. So you're going to have a resistance per meter. So it's got a resistance, R prop. Can you see it in the back of the room, guys? That's just a resistance per meter. Something else happens. These two wires have some insulator. Y'all with me? Anytime you have a plus minus voltage between any two conducting objects, you have a certain amount of capacitance per meter. Are you with me, everyone, on that? So now you're going to have a capacitance per meter. And not only that, now remember, we're talking about an actual transmission line. And also, you're going to have something, we don't term that resistance, we term it conductance. Do you remember the term conductance from, it's a conductance between the internet, from circuits? Conductance is 1 over resistance, all right? We use that because if you think about it, and I'm just going to bring this up because I think it helps really clear up a lot of things that you're wondering about. If you have a capacitor, right, as such, and you want to know the current flow here, I, for a given voltage, plus or minus V, you know C dV dt is equal to I, right? And the typical way we deal with this is we go to the phasor domain. Now I'll talk about the phasor domain in a second, but remember in the phasor domain, the ddt becomes a j omega. Does everybody remember that? If we go to the phasor domain, so we get this, we get j omega, right, times c times v is equal to I. Typically they do this for phasors. And then you can see that the impedance of this thing is simply equal to, if I take, I'll do it this way. If I take I over v, it's just j omega c. That would be susceptance. If I take v over I, it's simply 1 over j omega c. I'm just doing this to make sure you understand this, right? But basically, this is it. And if I take a look at this, and I want the amount of current that would flow through here, well, I'll get to that in a second, but the current would just be equal to j omega c times v, would be the amount of current that would flow through here. And you'd also have a conductance here. sorry. He uses the term G prime. Let me just explain this. When you talk about conductance, normally you're used to saying this. You have some V of T. That's a resistance. It causes an I of T equal to V over R, right? Right, class? Conductance is 1 over R. So here, it would be just V times G prime, if this is the prime coordinates. You all with me in this class? How many remember conductance? You don't use it hardly at all. You remember it from circuits or not? How many do really? It's rarely used, but it's very useful. You're going to find out for certain engineering applications because the notation allows simplicity. So just trust me on that one for now. Yes, sir.
So it's 1 over R, so, but it's important to have both the conductance and resistance.
And I gotta explain something. This resistance is associated with copper wire.
Okay.
This conductance is associated with the insulation.
Okay.
So normally, if it is a quote lossless cable, resistance would be approximated as 0, and I think you can all appreciate that for copper. And insulators usually have an infinite resistance 1 over that would be 0. So both G and C would be 0 for an ideal, and we'll get to that transmission. Go ahead.
Are you using conductance and admittance interchangeably since there would be an AC current there?
Well, conductance has to do with the real part of the curtain, right? We'll talk about susceptance and admittance and stuff in a bit, but just realize that G is just 1 over the resistance between the inner and outer conductor per meter. That's all it is. Now, if you look at this, and here's what I want to get today. I just want to tell you, we're trying to approximate what goes on in a transmission line as long as the cross-section is constant. If that's the case, then the resistance, the inductance, the capacitance, and the conductance per meter will never change. Y'all follow me? That's the idea. So if you look at this right here, you're going to have a voltage here, and I'll just put it as V of Z, and I'm going to work in a phase domain. All right, so I could write the differential equations, but I think you like phasor domains, right? Because the J omega L and 1 over J omega C, they really prevent a lot of problems. So over here, if you take a look at this, the impedance of this thing would be J omega L. Y'all with me? I'm putting it. The impedance of this would be simply R. The impedance of this, well, I'll tell you what, I'll leave this right here for a second. And now if you look at this right here, I want to do one thing. I want to make sure I explain this correctly. You take a look here, there's some delta I that's going to flow this way. If you look here, between here and here, you're going to have a delta voltage. Y'all with me? You're going to have a delta I, there'll be the current that shunts down this way, and you'll have a delta V, which would be the actual voltage difference between these two things. And we always do this over a delta Z, only because this thing will become a differential equation in a second. Everybody appreciate how we develop this. This is for a transmission line, and it will replicate for, this would be a model for any transmission line that's out there. From coax cable to anything you can think of, all right? Okay, now if you take a look at this for a second, the way I've done it, right, you're going to have a certain voltage drop between those 2 points. Do you agree with that? Just as the current flows. Everybody agree with that? It would be a loss. So the first equation of importance is going to be dV dz, and I'm going to call this the z coordinate. dV dz is going to be minus, the minus sign because it's a loss, the voltage is going down. And it's going to be R plus R prime J omega L prime times I. And I'm not going to put V of Z and I of Z, it's implicit because of the coordinate system. Y'all with me, class? That's the first equation. The second equation, remember that voltage drop is going to seem minimal, so you can assume that between here and here, you actually have V of Z, or we can put those on this side. So now we're going to get a di dz. All right, that's the amount of current that shunts this way. It's also a current loss, right? Because the current that's left going that way is going to be less. Do y'all follow me? So di dz will be minus And if you think about this, well, if I know V of Z, the current flowing through there is V of Z times G, because G is 1 over R, correct class? And the current through here is just J omega C times V. So over here, I put G plus J omega C, and it's times V. Now, both V and I are dependent on Z. Everything else is a constant, doesn't change versus position. It's important to appreciate that. Can y'all follow me on this so far? All right. Now, I want to get one equation with one unknown and then solve it for the general equation, the general form of the differential equation in a second. I need to erase this over here. Can you all hear me okay, by the way? In the far back, can you see this okay? Okay. Just yell if you can. So, to get one equation with one unknown, this is the next part of the deal. I'm going to erase that too. Get some better erasers. All right. To get one equation with one unknown, start with the, really, can anybody see a way to do this? You're not used to thinking this way. I got two equations, both differential, right? I and V appear in one. I want one equation with either just I or just V. This is something you keep in the back of your mind always. Always look at taking another derivative or another curl or divergence of either one to see what you can do. What if I take another derivative of this one with respect to Z? Then I get what? I get second derivative of V with respect to Z. Y'all see that? Is equal to what? Minus quantity R plus, this is R prime, J omega L prime, right? That's times dI dZ. Y'all see that, class? I just took derivatives of both sides. You agree? Everybody see it? What might I do to get rid of that dI dZ? Look at the next equation, right? I take number 2 and I stick it there. So that means I get this. I get the second derivative of V with respect to Z squared is equal to its minus R prime plus J omega L prime. And then dV dZ, well, there's another minus, makes this plus. And it's G prime plus J omega L prime times V. Can you all follow me? Let me see this right. Again, making one equation one unknown. Now, as engineers, we always do this. We simplify as much as possible. This thing right here is a pain to keep right. So what we do is we create something that indicates that, and it's a shortcut. It's called gamma. This is called the propagation constant. And the symbol for it is gamma, and it's equal to the square root of R prime plus J omega L prime times G prime plus J omega C prime. And it is also alpha plus J beta. Now, I'm going to talk about this for a second. Again, what we've done is created a constant, so I don't keep having to write that over and over again, because it's a pain. Y'all follow me? And as engineers, we always try to, anytime you're going to repeat something that's long, it just keeps repeating. Make a constant, and just use that. Now that's called the propagation constant. Alpha, right here, is called the attenuation constant. And beta is called the wave number. Now, because they have to have the same units, right? Do y'all agree with that? If you have A is B plus C, A, B, and C must have the same units in order to add them. You can't read my writing. You're not alone, I can't have it. This is attenuation constant here. And this is called the wave number. It's got other all the other things. Now, the attenuation constant has the units of Napiers per meter. The wave number has radians per meter. At first, it looks like these two make no sense. A radian and Napier are unitless. They mean, Napier per meter means an attenuation variable. Radian per meter is what? Phase change, isn't it, class? Radian's phase. Y'all with me? Okay. So, when you have your book, you'll see these things, and Dr. Whitler's book, and he defines it. But honestly, they're constants. Now, something I'm just going to mention right here. If you have a lossless, if we assume the transmission line is lossless, in other words, the resistance is zero, there's no heat dissipated, and G is zero. There's no current conducted that's going through a resistance of sorts between the inner and outer conductor. Then alpha will be zero. There is no attenuation. The only way the signal attenuates is by heating, really, thermal heating of the material that's flowing through. Y'all with me, class? I'm just mentioning that now. So getting back to this right here, this is the part we pay attention to. It's important. Now I'm going to replace this with gamma, and I get the second derivative of V with respect to G squared is equal to gamma squared times V. You all follow me on this? I'm just replacing the constants I defined. You with me? Can you all see that in the back, guys? Now that's a simple differential equation. What I'm going to do is erase this and come over here. You're going to see this isn't bad. Right? Spending a lot of time just making sure you understand how this comes about, why we're doing what we're doing. All right, over here we can take this equation. When we get one equation, we get the second derivative of V with respect to Z squared minus gamma squared V is equal to zero. Now remember, V is a spatially dependent coordinate right there, but it's in the phasor domain. We've suppressed the J omega term. So how do you solve that differential equation? This should be a second derivative of Z right here. Sorry. Well, you could do it. How would you do it? Say you go for a job interview, the guy interviewing says, solve that differential equation. How would you solve it? It's a simple first order or second order differential equation. It's homogeneous, right? They'll ask you this stuff at job interviews. I mean, things like this, not this question. All right. I mean, you're electrical engineers. How would you do it? Don't say Google it. You won't get the job. All right. Normally speaking, there's two ways, right? Either you can use an integration factor or an assumed solution, or you can do a Laplace transform. You know both of them, right? If you do an integration factor, you assume the solution is going to have a certain form. Since it's a simple linear second-order differential equation, you can assume the solution has the form e to the what? E to the lambda z, and then take derivatives and see if in fact your guess is right. Do y'all remember doing this class? How many remember that one? How many remember Laplace transforms? All right. Laplace transforms, you do Laplace transforms on both sides. On the side with the second derivative, you get s squared v of s, right? And then you're going to have what? Minus s times v of 0 minus derivative of v with respect to t at 0. Do you remember that? Is equal to the other side, which is just going to be, it's just going to be v of s. And then you go ahead and you group them and solve for it. Do you all remember doing that kind of stuff, Laplace? You're going to use Laplace transforms all the time. And as an engineer, you're going to be doing a lot of that. Anyway, it doesn't matter what you use, either one. The solution is going to be this. V itself, as a function of z in the phasor domain, will be some v0 plus e, right here. It's going to be to the minus gamma z plus v0 minus e to the plus gamma z. Now, I'm going to make some comments, and I want you to make sure you write that down. If I go ahead and replace gamma, and I'm going to leave it up here for now. So gamma is equal to the square root of r prime plus j omega l prime, g prime plus j omega c prime right here. And it's also equal to alpha plus j beta. If I replace gamma with alpha and beta, I get V of z equals V0 plus e to the minus alpha z, e to the minus j beta z, plus V0 minus e to the minus, or e to the plus alpha z, e to the plus j beta z. This may seem a little foreign to you. It's in the phasor domain. We have suppressed omega, the e to the j omega. But I want you to just write this down. This right here is a wave traveling in the positive z direction. And I'll show you why in a second. This right here indicates a wave traveling in the minus z direction. Now, I'll show you why in a second. Just write it down. And that's normally the case. We're going to have both a forward and a reverse traveling wave possible. Now, if you look at this right here, that's V of z. And I'm going to take you to the next step, but I need to back up a little. You remember how back in the day when you had circuits, and you said that if I get, and I'm going to give you a classic problem. Suppose I said this is another job interview question. Suppose they said this is 10 cosine of 20t volts right here. I have a resistance R. Actually, let me make it just V0 here. I don't want to use an actual value. I'll make this V0 here, and I'll just make this omega t. That's R, and I have an inductance here. And I'm going to assume the inductance is L, and they want to know the steady state equation for current. Y'all follow me on this? This is where phasors come in. So I've given you a voltage, just V naught cosine of omega naught t. Given you a resistance, given you an inductance, I want a general equation for I of t, assuming it's been on for a long time, not the transient portion. Y'all with me, class? How do you do it? Well, what's one way? One way is what? You could write a differential equation. You could say V0 cosine of omega t is equal to what? R times I of t plus L times di dt, right? And you could solve that way. You'd have to solve a differential equation, probably using Laplace transforms or maybe Fourier transforms. I remember doing something like that. How many had signals and systems? Who has had signals and systems? Raise your hand. Who has not? I thought that was a prereq for this course.
It's a codec.
Co-req. Oh, boy.
Most of us are.
You're in for fun, kids. No, I mean, signals and systems, of the courses you take, probably it is the most important to follow in your career as an electrical engineer. You use Fourier, Laplace, you use Z transforms, you use convolution. Your whole life's based on this. By the way, I might as well just throw this in there while I'm at it. So in all the realm you live in, everything is describable in the natural world by what we call integral differential equations, combination, or difference equations if they're quantum values, all right? All the world, all engineers do is cleverly come up with how to manipulate those equations and stuff to understand how to solve a problem, either maximize or minimize something. Usually, and I've had this happen here, a lot of people hated diffie cube, or they hated linear algebra. Do you realize that's the whole thing you're doing for the rest of your life is going to be based on that, unless you're in sales. I mean, car salesmen don't know mechanical engineering, they can sell cars. If you're an electrical engineer and a computer engineer, your whole career is based on that. If you hate that stuff, you probably don't want to be here, because that's going to be the next till you die kind of deal. Just telling you. Don't believe me? Go read about it. It's true. Anyway, that would be one way, right? Now, you could solve it doing Laplace transforms, right? Or Fourier transforms. Y'all had Laplace transforms, right? You had math. The math course is had to touch on that. Right. That's one way. Would you do it that way? How would you do it? Is that at a constant frequency? It's a quiet class usually. Of course it is. Big idiots. I mean, I'm assuming omega is a constant. If it's a constant frequency, how do you solve a problem like that? What do? We replace this with just a magnitude voltage at an angle, right? Instead of cosine dependence. So we replace this with simply V naught at 0 degrees volts. You all remember doing this, right? What next? Do we do anything to the resistance? What about the inductance? Everybody's like, oh, it's tricky. Don't say what you mean. Just J omega L, right? Isn't that the impedance of an inductor? I'm going to remember this, right? Did anybody not take circuits in here? Because if you didn't, it can't be anything. It's assuming you know circuits. All right, so this is J omega L, right? Now we're in the phasor domain. You all with me? Phasor is something where we assume the thing's oscillating or behaving in a way that's it's periodic. It's a cosine type of form. Everything's good. It's a linear system. All right, now this is a phasor current. How do you get the phasor current then? Anybody. It's that easy. Anybody. Series impedance, correct? Sure. That's all it is. You would say now I would take my V0 and angle 0 over R plus J omega L, and lo and behold, I would have a magnitude and an angle. Do you all agree with that? This is phasor solution to a differential equation. It makes life easy when you have a constant, either cosine or sine, as the excitation, because you don't have to write the differential equation to solve it. So this is going to have some value, I naught, and it will be at an angle. It'll be at e to the j theta I. I hope you all appreciate that, right? That's in the phasor domain. The boss is asking you a question about the time domain solution. Now again, this is assuming it's been on a long time. I'm not going to talk about transients here. How do you get the time domain solution? This is the part where a lot of people don't know the answer to this. This is very important to do, so listen up. How many know? Don't answer me what it is. How many know? Okay. If you are in the phase, he better know. He had this lecture on. If you're in the phasor domain and you want to go to the time domain, here's the general formula. If I want I of t in the time domain, I take this. This is a symbol for taking the real part of what's in here, of e to the j omega t times I phasor. Well, I phasor is some magnitude I naught e to the j theta. Now you all see I just took that and stuck it in, right? It's the real part, but you have to multiply that into the j omega t because now we're going to activate that. We're bringing the omega t, you might say, the function of omega t back. We want the time domain. So what happens here? Well, I of t is the real part of what? It's of I naught, which is a scalar, so you can take it out in front, e to the j quantity omega t plus the actual phase angle theta I. Now again, I just grouped the exponential components. Y'all follow me, class? Can you all see this in the back and stuff? All right? Now, when I talk about a real part, I have to do this because I've learned over the years that a lot of people just don't know this like the back of their hand, but you have to. When you take a look at anything, e to the j theta, that's something that has a magnitude of 1 at an angle. It's in a complex plane. This is equal to cosine of theta plus j sine of theta. You all follow me on this? What's the real part? It's the one that doesn't have the j in front of it. We would use I for imaginary, but because I indicates current in electrical and computer engineering, we always use J. In math, they'll use I. In a lot of physics, they will too. You with me, class? The real part is the cosine. So if I would expand this, now just take a look. I got e to the j omega t plus the phase angle. I would get a cosine of omega t plus the phase angle plus j sine of omega t plus the phase angle. You all with me? The real part is just the cosine. So that means I of t here would just be I naught, which would come from that. This is just going to be the magnitude of that, times cosine of omega t plus the phase angle associated with I. That would be the time domain solution for the steady state component. In other words, not the transit. Now, if you had a switch there, we'd have to do this a little differently because now we have to bring in the transit component. Y'all remember doing that kind of stuff? And it probably in your math courses, but all right, y'all with me on this one? Now we go back here what I'm getting at here, all right? This is in the actual phasor domain. We're going to take it to the time domain. Y'all with me? All right. I'm going to do it over here. So what am I going to do? Well, I'm going to just write this down. So when I want to get the voltage into the time domain, I say now V of z comma t would be the real part of, and it would be e to the j omega t times all this. Y'all follow? You don't have to write it down, but just watch. So now I have V0 plus e to the minus alpha z, e to the minus j beta z. And it's going to be plus V0 minus e to the alpha z, e to the plus j beta z, right here. And I want you to take a look at something. Just listen. You see how I have that e to the j omega t, and it would group with this e to the minus j beta z. Do you all see that? Right? The alpha there is real. That's, you don't do anything with this. So if I take a look at this, this part, V0 plus would come out. I would have e to the minus alpha z. Then I'm left with e to the j omega t minus beta z, right? When I take the real part of that, that's just the cosine. So it's going to be cosine of omega t minus beta z. When I do the same for that part, I'm going to press for time, I'll get plus V0 minus e to the alpha z, and it's going to be times cosine of omega t plus beta z. And this would be Vz of t. Now this indicates a positive traveling portion of the wave, and this the minus travel. Can you all follow me on this class? I'm just trying to be clear about how you get the phasor domain, from the phasor domain to get to the time domain. Y'all were with me in class? Raise your hands if you are, so I know. All right, in the back? All right, now, how do I know that's traveling in the positive z direction? Any guesses?
Because
Something where we track the phase, and we're going to get, you probably know it, phase velocity. Now look at this. You see this term right here? That is an angle. Call it theta. It doesn't matter what you call it. You with me, class? An angle. Omega t minus beta z would be an angle. You with me? If I take a derivative of that angle with respect to t, I go ahead and I'm taking with respect to t. Here I get what? Omega, the derivative of t with respect to t is 1 minus beta times dz dt. Now here I got to make a point. So phase velocity, phase. How do I relate phase? You've all seen waves on the ocean, right? Moving. If you're on the crest of that wave, it is at a constant phase point. Do you all follow me on that? Think of a surfer. He wants to be just in front of the crest. Well, that's got a constant phase point. So how fast is that constant phase point changing? If we take this derivative and we set it equal to 0, we can get the phase velocity by looking at dz dt. You all see that? The rate of, like, what, you're familiar with dx dt. Remember in physics? dx dt was what? Velocity, right? First derivative. dz dt is velocity too. So that means what we call the phase velocity. Phase velocity is Vp, and it's really going to be equal to, if I take the omega to the other side and divide, I get it equal to dz dt is equal to omega over beta. Now block that down. That's critical. But you notice how it's positive. See that? It means it's going in the positive z direction. What about this one? In your own words, what do you see happening there? Well, if I set omega t plus beta z equal to the phase and took a derivative, and then rearranged it, I would get something with a negative component. All right? That's how you know one's going one way, the other's going the other. Do I get a minute or two left? 1 minute, 2 minutes. Let's see a mob out there. First day of class goes. All right, that's phase velocity. You with me, class? Now, in keeping with that, There's one thing that's real important. You know this from physics. How do you get things related to wavelength or period? You remember that? Wavelength and period. You're going to get it, right? I don't know if I have time. How much time do I have? Because I got a lot. What? 15 seconds. 50.
It's yeah.
All right. I'm going to cover this next time. I'm going to give you some reading, some homework, some of the stuff we didn't get to, but I'm going to assume you're going to get a crack at it, so you come in with questions in your hand. On Friday, we don't have a quiz this Friday. But I will go over some of the problems. And I'm sorry I didn't get further, but I really want to make sure I clear up anything that has to do with phasers. Phasers, I've had nothing but trouble with.